Hello and welcome back to the Quantum Information Reading Seminar, where our goal is to read the paper Black Holes as Mirrors by Hayden and Preskill. In the last video, we spent a long time calculating an integral over the harm measure. The objective there was to prove the bound, or the main bound of the paper, the one which is exploited to derive the main consequences of this paper. So that's equation 4 here, which we see here. Now in the previous video we didn't quite get to proving this bound. In fact, I introduced a method to calculate measures of the Haar integrals and calculated one of 4 necessary integrals in order to obtain this advertised bound. Now I should state that in the previous video I believe there's a missing factor coming from a loop that I did not include. Also, there were 3 other integrals that I didn't calculate. So in the past weeks offline, we've been looking at those integrals and assessing whether or not indeed this approach does give a path forward to proving the main bound of the paper. I think our conclusion is yes, indeed, it is possible to prove a bound similar to the main bound of the paper, but actually the method I described in the previous video will supply slightly improved bound. I think there will be additional factors on the right which just slightly improve the bound. It won't change the consequences of the paper. There's no really any reason to prove the improved bound that this method I described in the previous video could give you. It's just nice that you indeed can slightly improve the bound on the right hand side, and to understand why the bound of the paper here is in fact not completely optimal, you have to really take a look at the references that were cited, which gave the derivation of the bound in the equation 4. And you can see that in those references they use similar techniques to calculate Haar measure integrals, but also additionally they apply some inequalities, a Cauchy-Schwarz inequality notably at some point, and that slightly weakens the upper bound in references 15 and 16, and because of the special structure of the problem we have, we can do ever so slightly better. As I said, it doesn't lead to a material difference when considering the consequences of this paper, but it is kind of interesting to know that you can slightly tighten up the bound in this paper. Okay, today's goal is really to start looking at the consequences of this main bound. So the main bound, equation 4, is a statement about how close the reduced density operator for Charlie and for the black hole prime system, how close that density operator is to a product density operator. But it's actually a little bit more. If we start reading through the paper at this point, we'll see that it's not just saying that this reduced density operator for the Charlie black hole remainings part is nearly a product. It's in fact saying it's nearly completely mixed. So let's really see that here. So I'll start reading from the end of equation 4. Here sigma n VB equals the trace over B prime of sigma n B prime VB is the marginal density operator on n. And sigma B prime max, which is just the maximally mixed density operator on B prime. The L1 norm defined by this equation here is an appropriate measure because 2 states at close in this norm cannot be well distinguished by any measurement. So this is making a reference to the Holovo-Hellstrom bound for the probability of distinguishing 2 states. You can express the probability that you can optimally distinguish 2 states in terms of this trace norm distance, A1. In the case we are currently considering, in which B is maximally entangled with NE, rho NB is maximally mixed on a system of dimension B divided by N. Okay, we should probably spend a couple of minutes discussing that statement. But first I just want to point out something that a simplification in the notation and equations here, which can be a little bit helpful when understanding this bound in equation 4, namely sigma n of VB. So that's a quantity that appears in the equation 4 bound. What is that? Well, that's Charlie's reduced density operator. And we know something about Charlie's reduced density operator. Since Charlie shares maximal entanglement with initially with Alice, we know that that's proportional to the completely mixed state, right? So that's just something that's not, I mean, it doesn't sort of pop out at you when you're reading this paper. It seems like it, and I'll show you the picture, right? At the beginning, time is 0. Charlie, who is in possession of this subsystem N, shares maximal entanglement with Alice. And then some black hole dynamics occurs. The black hole dynamics is local to the Alice rest of the universe system, and therefore doesn't affect the entanglement between Charlie and the degrees of freedom that Alice originally possessed. Therefore, Charlie's reduced density operator was, and will always be the completely mixed state. And that's something that's sort of pretty helpful to have in mind. I mean, here it looks quite complicated, this formula, but actually it's just the completely mixed state. All right, so then we're now talking about rho NB. And there's a statement that rho NB is maximally mixed on a subsystem of dimension b divided by n. And we should now understand that statement there. So what's rho NB describing? Rho NB describes Charlie's qubits, and it also describes the black hole degrees of freedom. So that's somewhere here, I believe. So rho NB is defined. And apparently it's completely mixed at the time t is 0, well, the initial time for this scenario, on a subsystem of dimension n, b divided by n. So let's try and understand that. So we have this density operator, rho NB. Remember, this is the initial state of the whole story. Rho NB comes from the initial state after a partial trace. So remember, Charlie is maximally entangled with Alice, and the state at the beginning of all of this is also assumed in a maximally entangled state. So let's just now take a look at this. This is the picture that we're meant to have, and here's sort of B here. I'll draw it in a different color. Here's B, and here's N. And we're now asking the question, like, how mixed is the state rho NB? Well, we have to talk about the dimension of the quantum system NB, or the quantum Hilbert space for NB. Well, that's easy, right? That's just the dimension of the Hilbert space for NB, the degrees of freedom of N and B, is by per definition sort of using this notation of Hayden and Preskill, mod NB, which is also just the product of these two dimensions there. Now, if you look at the pure state, if you look at the reduced state rho NB, where does it pick up? Is it pure or is it mixed? Well, it's mixed. It's mixed because there's entanglement that's between the B system and the rest, right? There's this, I'll draw this red line here indicating this, we're tracing through a maximally entangled state there. But it is, there's a lot of purity. I mean, the state isn't completely mixed because there's a full pure state there. NB contains the maximally entangled state. Or does it? B is maximally entangled with NE. I've mixed up degrees of freedom here. think. No, let's go with this. I think this should still be correct. Find out, hey? So we've got a the reduced state rho NB is what you get when you trace out E of psi. And in the notation they're using, we have psi B and E. B and E. Psi B and E. So that's what rho NB is. It's what you get when you trace out E from the initial state psi B and E. But the initial state psi B and E is really itself a product. I mean, it's a product of entangled states. So there's a maximally entangled state. Let's see what notation they use here. Okay, they just say the words maximally entangled. Well. Okay, so then we'll have some kind of tensor product structure, right? Because we've got this maximally entangled state between Alice and Charlie. And then there's another maximally entangled state, called phi prime, say, between E and the black hole degrees of freedom, EB, say. And so we've got this structure here, and then when you take the trace over E, you're breaking a maximally entangled pair, maximally entangled state, but also you're not breaking some entanglement. So the entanglement that Alice and Charlie share is not broken. Alice and the black hole, right? So for the purposes of this discussion, right? Everything that Alice owns is now is immediately assumed dropped into the black hole. So the blue in maximally entangled state isn't actually broken by this partial trace. We're not tracing over any degree of freedom here that was initially entangled between Alice and Charlie. We're just tracing over the environment black hole entanglement in yellow. So the result of this partial trace will be some kind of mixed state, right? So, just after the partial trace, we're breaking this maximally entangled state here. We're losing information about half of the maximally entangled pair. And we've got some kind of posterior state on the black hole degrees of freedom. And this is the black hole just pre Alice throwing in her qubits. And so we got some kind of posterior state here. What should we call it? Tau, right? So we got some posterior state on the degrees of freedom of the black hole just prior to Alice throwing in her qubits, and we've got a nice pure state on Alice's degrees of freedom and Charlie's degrees of freedom. And so how mixed is this? Well, it depends on how many E bits we broke when we partially traced out E. And if we look at this, refer to this picture here, then we see that this dimension of the system left over has to do with the environment and the number of degrees of freedom of the black hole just prior to Alice throwing in her degrees of freedom. And can I find that number quickly? So rho NB is maximally mixed on a system of dimension B divided by N. Right, so the idea here is that you've got pure state on the AN degrees of freedom and a completely mixed state. I mean, we're tracing through a maximally entangled state here. So we know that the mixed state that you get when you trace over maximally entangled states is always completely mixed. It's completely mixed on on a subsystem, and we want to work out roughly, we want to work out exactly what is the dimension of the subsystem upon which T is maximally mixed. And well, we're going to do this by dimensions essentially. So B, mod B is the number of degrees of freedom in the black hole after Alice throws in her system. And the total number of degrees of freedom of the NB system, how many degrees of freedom do we have? Well, that's easy, right? It's just the dimension of N, the dimension of B. And we want to understand how many degrees of freedom are actually still entangled with the environment just immediately after Alice throws in her degrees of freedom. And to work that out, we realize that N of B, how many degrees of freedom are entangled with the outside environment E? That's the question we're trying to answer here. And since B is comprised of some degrees of freedom that are maximally entangled with Charlie, namely N degrees of freedom, so B is comprised of degrees of freedom entangled with Charlie, tensor degrees of freedom entangled with E. So how many degrees of freedom in B are entangled with the environment? Well, we know they're maximally entangled with the environment, and the one way to get at this number is to simply realize that B, the dimension of B is the dimension of B prior times by N. Why N? Because every one of Alice's qubits is maximally entangled with one of Charlie's qubits. And then to extract the number B prior that we're interested in, we should simply divide by N, right? So the dimension of B prior is just B divided by N. Goodness, I hope that's the same as what they write here. Yep, it is. Fantastic. So we now know that the number of degrees of freedom that were in the black hole entangled with the environment prior to Alice throwing in her qubits is equal to dimension of B divided by dimension of N. Therefore, we have a maximally entangled state, but we have a maximally entangled state between these prior degrees of freedom and the environment. And if you calculate trace of rho NB squared, well, let's go up, right? So what is trace of rho NB squared? Well, we have this nice formula here now for rho NB. Let's work out the trace of rho NB squared using that formula. So it's the trace of tau B prior squared tensor. Well, when you square a pure state projector, you get back the pure state projector. So that stuff remains the same. So this is, what did I call it up there? AN, yeah? So I've just squared rho NB, and I've got this pure state projector, but when you do a trace over tensor product subsystems, then that's equivalent to the trace over B prior of tau B prior squared times by the trace of over AN of this maximally entangled projector. That's a pure state. The trace of that thing is 1. So we're left now with a trace of a B prior tau B prior squared. But remember, tau is maximally entangled on a subsystem. It is maximally entangled, which means it's just a completely mixed state divided by the dimension of the system that it finds itself squared. And when you work out that trace, well, you square the bottom. And the identity squared is the identity squared. The identity squared is the identity. Trace of the identity is just the dimension of the space it acts on. And so we end up with our formula for the purity of rho NB, which is just the dimension of B prior, but of course we just worked out or argued that that dimension is none other than B divided by N. Okay. Wait on, I made a mistake, didn't I? So it's 1 divided by the dimension of B prior, which is just N divided by B. Let's check. Indeed. Okay, so all is well. We can recover that formula. And now we're going to apply this observation here in the right-hand side of the main inequality to actually start getting some numbers attached to all this stuff. Okay, so then let's take this inequality, see if I can remember it in one go. Sigma NB prime minus sigma N sigma B prime max. I'll have to refer back to it a couple of times, I'm afraid. Sigma NB prime minus sigma N tensor sigma B prime max 1 squared is less than equal than NB over R squared. And then there's this trace of rho NB squared. We just worked out what that is, right? Just substitute that in. I'll just rewrite this dimension formula here slightly. Substitute in now what we know for the trace of rho NB squared, namely that it's N divided by the dimension of B. These B's cancel. And now we have, oops, that's actually an equals sign. Now we have N squared over R squared, right? And that's the advertised bound here in the paper. So of equation 4, the right-hand side of equation 4 becomes the dimension of N squared divided by the dimension of R squared. Now we substitute in the numbers that we have for those dimensions. So N, Charlie had K qubits, so the dimension of N is 2 to the K, and 2 to the N squared is 2 to the 2K. Similarly for R, according to the way we define things, the dimension of R is just simply S qubits, which is given by K plus C, where C is the number of radiated qubits. And so putting in those dimension factors here, we can recover this number here. And so the important thing to note here is is that this right-hand side gets extremely tiny, extremely tiny for large C. And how large are we talking about? Well, like C is 10, right? 2 to the minus 20 is already a pretty small number. And you can imagine that it doesn't take long for a black hole to radiate effectively 10 qubits. And now, black holes are these gigantic things radiating stuff all the time. So for this number on the right-hand side to become astronomically small, then you only need a handful of qubits to radiate. So we see that for a typical unitary transformation VB, that means, remember VB is the internal dynamics of the black hole. And for C sufficiently large, the state of NB prime is nearly maximally mixed after K plus C qubits have escaped from the black hole. Alice's K qubits have been forgotten by the black hole and have been acquired by Bob. So let's go back to this picture. Here's the black hole, in come Alice's qubits, and then some time later, the black hole is radiating. Remember, it's radiating all over 4 pi radians. And after K plus C qubits come out, then the state, and this is the important point, the state of NB prime is nearly maximally mixed. Now that's sort of said in words here. It is actually a consequence of this equation 4. Let's see that, right? they didn't quite go ahead and explicitly write it out. Let's just explicitly write that out. So equation 4, now we'll substitute in all the information we have and just write out a version of equation 4 which is most helpful for now this story. So remember, equation 4 is the distance between sigma NB prime, the reduced density operator on Charlie's qubits and the black hole remaining qubits, and this product state here. But this product state here is really just the maximally mixed state. Because the reduced density operator on Charlie's system is maximally mixed. It always is, nothing changes there. And the definition of sigma B prime max is, well, maximally mixed. That's what it means to be maximally mixed. So what we found is that the distance between sigma NB prime, that's the state on Charlie's qubits and the remaining black hole qubits, is basically maximally mixed. Oops, 2C, for C large. I mean, the only consequence we can, there's no way to avoid the consequence. This applies for lots of, or let's say, yeah, I'll put it in quote marks, lots of, because we can't use the mathematically precise terminology almost all. So for lots of potential black hole dynamics VB, sigma NB prime is effectively, it has to be the completely mixed state. There's no other, we can't escape this conclusion. Because this integrand here is positive. And if you sum up a lot of positive numbers and they're smaller than some very tiny number, then each of those numbers had to be themselves extremely tiny, right? You know, the distance between sigma NB prime and the completely mixed state has to, you know, apart from an outlier here and there, has to be extremely tiny when C is large. So we learn that the degrees of freedom that Charlie and the black hole possess are maximally mixed. So this is, you know, after radiation, we've got Charlie, who's just there to simplify matters. We have the black hole remain. So the black hole remains B prime, and we have the environment. And what we've learned is that this density operator here, you know, partitioning our universe into 3 spaces, E, Bob, blah, 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 the rest of the universe, we've learned that the state on the black hole remains in Charlie, this space here is basically, for all practical purposes, completely mixed. Now, if something's completely mixed, and if a subsystem is completely mixed, but this whole system began in a pure state, evolved unitarily, then there's only one conclusion you can draw. That mixedness comes from entanglement. So these 2 degrees of freedom, 2 subsystems here, B prime and N, are maximally entangled with the rest of the degrees of freedom of the system. So that, you know, there's this maximally entanglement that's coming between N and B prime and the rest. That's the conclusion we have to draw. Inconveniently, the information originally encoded in Alice's memory has become encoded in a subsystem M prime of Re that is very diffusely distributed among the emitted radiation quanta. But, in principle, Bob could do a quantum computation that maps M prime to a compact system M hat localized in his laboratory. For any fixed value of the unitary transformation VB, Bob's decoding map can be chosen so that, after decoding, the density operator rho M hat N over M hat N is close to the maximally entangled state, M hat N, phi M hat N. See, for example, 16. Now, we've got to try and sort of decode all of this paragraph. So the story is, I'll try and draw a space-time diagram. So here's Charlie, here's Alice, here's the black hole entangled with the environment, then the dynamics occurs, and then we know that afterwards the B prime, what's left in the black hole N system, is maximally mixed with the rest of this universe, the radiation and the environment and Bob. And how can that be? That can only be if this initial entanglement here has been redistributed. This initial entanglement here has been redistributed to between Charlie and the rest of the universe. So the black hole acts as an entanglement redistributor, if you like. That means that every degree of freedom that Alice had has now escaped into the environment. That's the consequence of this line of reasoning. And now the discussion turns to how can Bob exploit that? Now that Bob can in principle access all the radiation around the black hole, I mean, he has built a Dyson sphere around the black hole. I mean, obviously, if Alice was going to throw some information into a black hole and she spotted a Dyson sphere surrounding a black hole, she might probably avoid that black hole. But nonetheless, let's not let that practical matter dissuade us from continuing this line of thought. The point is more that this is an in principle experiment to understand how black holes process information. It's not really intended as an actual protocol for destroying sensitive information. So Bob has now trying to recover Alice's qubits. He's built this Dyson sphere around it and he's collected the radiation. So all this radiation has come out. Now the thing is, this black hole is mixing up stuff. You know, you send the qubits in, the black hole mixes them up, it comes out diffusely in 4 pi radians in the radiation, that the Alice's qubits. And Bob has to somehow reassemble all this and bring it back to Alice's original message. Now, in principle, he can do this, right? If he understood the whole of the black hole, Bob, you know, what does Bob know? Bob has been given an extraordinary amount of power. Bob knows all the environment quanta, degrees of freedom, plus he knows VB, right? He's an amazing quantum gravity theorist. Given that it's in principle possible to reconstruct the state that Alice threw in, he just has to undo everything. That's all he has to do. And that's what this discussion in this paragraph is centered on. So Alice's degrees of freedom have become encoded in a subsystem M prime of Re. So Alice's degrees of freedom have ended up distributed in R effective. And how many degrees of freedom did Alice have originally? Well, n, right? The size of n. Have become distributed in R in an n-dimensional subsystem. We say the word subsystem, I mean those degrees of freedom are somewhere, they're distributed in this Hilbert space. And that's extremely, this subsystem is somehow diffusely located inside the radiation degrees of freedom. Now, Bob is free, he's possession of an amazing quantum computer that can do any unitary transformation that he so pleases. And Bob is therefore free just to swap all those Alice degrees of freedom to a convenient storage location. So he stores all the radiation quanta in some quantum memory, then he applies all swap gates to move those degrees of freedom to a smaller compact system M. And that's localized in his laboratory. For any fixed value of the unitary transformation VB, Bob's decoding map can be chosen so that after decoding, the density operator rho m hat n of m hat n is close to the maximally entangled state. Okay, that's just simply saying that Bob has undone the unitary transformation VB on the degrees of freedom that Alice threw into the black hole. He's reconcentrated the entanglement. So here we'll redraw this space-time picture again. Here's Alice, Charlie. Here's environment, black hole, degrees of freedom. Then we do the black hole dynamics, and then the radiation comes out. We're left with the remaining black hole degrees of freedom. We're left with Charlie's degrees of freedom. And then Bob comes along. What does Bob do? He reconcentrates that entanglement. So that entanglement that the black hole has spat back out onto a nice m-dimensional subsystem. So he just redefines the subsystems somewhat. And then what do we know at the end of the story? After Bob has acted, we have that we've concentrated all the entanglement that Alice initially shared with Charlie. All that entanglement gets concentrated into a subsystem M prime, and there's a posterior radiation subsystem R prime. All that's happening is we're redistributing entanglement, right? We're not decoding anything. We are decoding something in that we've redistributed the entanglement. Now, we can estimate how close the entanglement of the final state after Bob's decoding is. You know, how much entanglement is there? Well, there's a bound here. How good, or let's say how well, can he concentrate or recover the entanglement? Between Charlie's qubits and the radiation subsystem. Well, for that we want to measure the fidelity of the state. So rho m hat n is what, that's the result of Bob doing his redistribution. And we say, how close is that to the maximally entangled state? That's just the fidelity I've written up here. How close is that? Well, we need to bound that quantity, and we have a lower bound for that quantity, and we have a reference for that lower bound, namely paper 16. Let's have a look at paper 16. I feel like this shouldn't be difficult, but maybe there's something I'm missing here. Decoupling approach. Okay, that's the decoupling paper. This may need to chase down the contents of the reference in order to understand this bound. Okay, I tell you what we're going to do is, this video is already getting quite long today, is we're going to pause at this. No, we're going to read on. We're going to assume that this inequality is correct. We know what that number is on the right hand side, and then I'll get back to you in the next video about whether or not that's a difficult proof for that or not. Well. We'll take a look at definitely in the next video equation 7. So equation 6, but we will continue reading to understand the consequences of this bound. Equation 6 implies that after averaging over VB, the fidelity that the recovered entanglement differs from maximal by more than 1 is no more than 2 to the minus c. It's an astronomically tiny number for large C. So apart from a small error, Bob holds the purification of Charlie's reference system N. That means he has captured all of Alice's qubits. Thus equation 6 can be well regarded as the quantum analog of the classic estimate. In both the classical and quantum models, the information that Alice deposits in the black hole escapes almost as soon as it possibly can. We can also, it's worth reading on here to get a heuristic discussion of this. Sometimes these heuristic discussions can be very helpful to understanding the equations when we go back to them. So the conclusion that sigma NB prime becomes nearly maximally mixed after about k randomly chosen qubits are discarded can be understood heuristically as follows. The initial density operator rho NB is uniform on a space of dimension B over n. So we've already proved that today. And so it can be expressed as a uniform ensemble of B, oh look, we found a typo. B over n mutually orthogonal pure states. That's what it means. If R, the size of the radiation system, is much smaller than NB prime, then a typical pure state on NB is close to maximally mixed on R. So, therefore, after tracing out R, each pure state in the ensemble representing rho NB yields a uniform density operator on a subspace of dimension R of NB prime. Altogether then, ignoring the overlap of these subspaces, the density operator sigma NB prime is nearly uniform on a space of dimension B times R divided by n. This matches the dimension of NB prime, because n times B prime is n times B divided by R, for R equals n. We expect then that for as soon as the radiation system is about the size of Charlie's system, the density operator of sigma NB prime is nearly uniform on NB prime. So this is a purely heuristic argument for why this result should be true. And I mean, you should always, if you're going to prove something, and you should always have at least a heuristic argument for why you think it's true, otherwise why are you even trying to prove it if you can't even convince yourself heuristically that it's true. Okay, so in the next video we're going to discuss the connection between this result and capacities of erasure channels, and then that discussion is likely to be less equation heavy and more discussion heavy. And then in the coming videos, I can predict that we're going to have a bit of a decay of our ability to understand the paper. So in the fourth video, we also have a somewhat discussion heavy section. In the fourth section, the thermalization time. In that section, the actual dynamics of the black hole and how fast those dynamics will be discussed. And there, this is not entirely, it's not entirely possible to quantify these dynamics and these mixing times. This is necessarily heuristic. And then, you know, as we continue through the discussion, we're going to get to more and more, we'll be basing our arguments on more and more conjectural results about black holes. And so the discussion will become necessarily sort of less and less concrete. There is some discussion on how to model the dynamics of black holes that is coming up. And then there's some discussion on whether or not you can think of black holes as cloners. We'll also spend a little bit of time on that, and then we'll eventually come to the conclusions. Having looked a little bit ahead, I can predict that we won't be able to really understand all the details of all these discussions. At some point, there'll be this sort of point of diminishing returns where we invest more and more time to understand a sentence, and we won't actually gain super lots of intuition or understanding out of it. This is largely a function in this case of the subject matter, which is we're trying to talk about the quantum mechanics of black holes, which is a theory that isn't quite completely finished yet. Nevertheless, we can learn quite a lot of fascinating information about black holes without actually even knowing these dynamics, and that's one of the sort of remarkable aspects of this paper. So that's it for today. Thank you very much for your time and attention, and I look forward to seeing you next time. Bye bye.